We are very happy to have Professor Debaruti Chatterjee from Ayuka, and she will talk about some neutron star astronomy. So I will hand it over to her to start.
Thank you very much, Arpan, and thanks to all those who are present, even though it's a Sunday afternoon. I will try to keep this talk as entertaining as possible so that, your Sunday is not ruined. So let me share my screen. All right. Just a second. Okay, so you can see the screen, right?
Yes.
Okay. So thanks to IIT Gandhinagar for inviting me to give this talk. It's my pleasure to be here today. So I'm Debaruti Chatterjee. I am an associate professor at Ayuka, Inter-University Center for Astronomy and Astrophysics. I'm also a key member of the LIGO India project and also member of LIGO Scientific Collaboration and LIGO India Scientific Collaboration. So today I'm going to talk about how gravitational waves can act as a tool for probing extreme physics. So I will first outline what I mean by extreme physics. So as, just a second. Okay, I think I'm still online. Yeah, all right. So what I meant by extreme physics is that we are looking into the building blocks of matter. We are trying to look into the densest forms of matter in the universe. So as some of you might already know, so this is the state of the art knowledge that we have from nuclear physics and particle physics. So we have a standard model, right? So what does this model tell us? It's that matter is made up of atoms. Again, this can be broken down into nuclei and electrons and protons. So the nuclei consists of neutrons and protons. And again, imagine looking into matter with an extremely powerful telescope. So what do you see? When you go further and further into the building blocks of matter, ultimately you see that even these neutrons and protons are built up of constituent quarks. So we can say that the ultimate building blocks of matter are leptons on one hand. So you can see these figures at the bottom. Leptons means electrons, muons, tau, particles, etc. And on the right-hand side, you can see quarks. So there are 6 flavors of quarks, and these compose all the matter that we see around us. Okay, so how can we probe this? As you can see that you need more and more powerful, more and more energetic tools to look into matter to see what are the fundamental building blocks, right? So first of all, we can imagine nuclear experiments. So with nuclear experiments, we can look into nuclei, right? Just a second, can you mute yourself? Arpan, can you mute? Yeah. Can you mute the participants? Yeah. Thanks. Okay. So, like I said, so nuclear experiments give us a fairly good idea about what nuclei are composed of. Okay. So you can see this figure. Again, there is. Okay, so let me try again. So if you can see this figure on the left-hand side, you see that this is the idea we have of the nuclear potential. So what does it tell us? It tells us that there is a short range repulsive core, which means when you go very close, at very close range, then the nuclear force has a repulsive nature. And at longer distances, it has an attractive nature. So this behavior tells us that there is a certain saturation behavior of nuclei, and also we can determine binding energies of nuclei from nuclear experiments. So nuclear experiments give us, so what is the saturation energy per particle, what is the density, and also the binding energies and so on. There are also certain experiments which help us to probe matter, which is not only, which is not at neutron proton symmetric nature, which means that most of the nuclear experiments we have in the laboratories, they have almost the same number of neutrons and protons, whereas there are some experiments which help us to probe what happens when you go to very neutron rich matter. Okay, so you can see that there is an experiment called isol trap experiment. You see this figure on the right hand side. You see that these experiments actually probe so this region, which is very far away from this beta stability line, which is the line where you have experiments at almost the same number of neutrons and protons. Okay, and there are also these experiments like which are called giant resonances or pygmy resonances. So what these do is they probe into nuclear vibrations, so different kind of nuclear vibrations, which also tell us about so something called neutron skin thickness, which means you look at the figure at the bottom, you see that there is a difference between the, say, the RMS neutron radius and the proton radius, and therefore this difference is called the neutron skin. So it's like a neutron skin surrounding the nucleus. So this can also be probed with some experiments. So all these tell us about the behavior of matter, which is not only at the same number of neutrons and protons, but also far away from it. So very neutron rich matter. What else? What other information can we have from terrestrial experiments? There are now these heavy ion collision experiments. You must have heard about CERN, which is the nuclear facility, the European nuclear facility at the French border, French-Swiss border. You might also have learned about some other experiments like Ganil facility, which is in France, and GSI in Darmstadt. So what happens in these experiments is that beams of heavy particles are made to collide, and then these stream out particles and forming a quark gluon plasma. And this is hot and dense matter. So this is also some experiment which helps us to probe the nature of dense matter. Okay, so these are all the different experiments that we can conduct on Earth to find out about the nature of the extreme nature of dense matter. But what if I told you that there are also certain astrophysical sites, astrophysical objects, which can give us much more information about dense matter? So exactly one of this kind of objects is called a neutron star or a pulsar, and this was serendipitously discovered by Jocelyn Bell, who was a PhD student at Cambridge University. So in 1967, she noticed some scribbles, strange scribbles in the radio frequencies that she was studying with her radio telescope while trying to observe quasars. So from this, she noted that these were extremely periodic pulses that were arriving from outer space towards the Earth. So initially, people even thought that these might be alien signals, but it was quickly understood that this is nothing but a pulsar, which means it's like a pulsating, it's a rotating compact star and giving out a strong electromagnetic beam along its axis. And every time this beam sweeps the Earth, it gives out a pulse. Okay, so these pulsars or compact stars are also one of like an astrophysical laboratory in space that can give us a lot of information about dense matter. How is that? So to understand this, we'll have to look at the origin of pulsars. So normal stars, like say that of the sun, or it can also be say up to 8 to 10 times that of the sun. So what happens there is that light stars like the sun, so the sun keeps burning because it burns hydrogen fuel in its interior, producing helium, and this balances this thermal pressure balances the gravity, and therefore this is a stable object, right? So what happens in more massive stars, say like 8 to 10 times as massive as the sun, this kind of fusion continues to produce heavier and heavier elements. So like hydrogen is burned to produce helium, and then consequently carbon, oxygen, silicon, and iron that you can see in the inset. But what happens is that now when, okay, I will play this once again. So you see that this is the cycle of such a star. And so when this fusion proceeds, it gives off energy, right? It gives off energy, thermal energy, which supports the star against gravitational collapse. But once these outer, okay, so once iron is formed in the core, what happens is that you can see here in the inset, so iron has the highest binding energy possible. And therefore, what happens is burning iron cannot produce any more energy. So here fusion stops, and therefore what happens is there is a collapse of the outer layers, forming, then ultimately nuclear energies are reached at the core, and there is a bounce and throwing out these outer layers into space. This is something which is called a core collapse supernova explosion. You can see these beautiful pictures. If you go to the NASA web pages, you can see beautiful pictures of supernova explosions like this. So this is the Crab Nebula, and the Crab, which is left behind after such an explosion. And so you can see here in this schematic figure, so this is this bounce and the outer layers being thrown out into outer space. And what ultimately is left behind is the core. And this core is what forms a compact star or a neutron star. So if we look at the life cycle of a star, so this is exactly what I mentioned now. So a massive star goes through these cycles, where ultimately there is the supernova explosion and the core forms the neutron star. But like I said, so why are we studying neutron stars? Because neutron stars are actually the densest form of matter in the universe. So these are like astrophysical laboratories in space that can